Good morning, ladies and gentlemen. Welcome to the second day of the Trainer Networking Conference 2007. My name is Karl Wietsch. I'm the Secretary General of Trainer, and it's my pleasure to be chairing this session this morning. In recent years, the Trainer Networking Conference always have a fixed schedule, and that implies that we have 6 keynote speakers speaking in plenary sessions, 1 in the opening session, 1 in the closing session, and 2 each in the early morning sessions on the Tuesday and the Wednesday. In some years, these plenary sessions have a theme. For example, there's the applications plenary or the technology plenary or the security plenary, but mostly that is not the case. And looking at the program of this year's conference, I think it's not the case this year. Actually, the title of this session is simply Plenary Number 2. So I'm not going to make up a complicated story trying to explain to you that the 2 speakers that we have this morning have so much in common. Actually, they're quite different, probably. One is a talented young researcher from the United States. The other is the grand man of the Internet in Japan. But maybe when we've heard them, we'll find that they have more in common than we thought after all. So while the people from the last bus are coming in, without further ado, let me introduce our first speaker, Kevin Almaroth. Kevin is a professor at the Department of Computer Science at the University of California in Santa Barbara, and his main research interests include computer networks and protocols, wireless networking, multicast communication, large-scale multimedia systems, and mobile applications. At UCSB, he is the Associate Director of the Center of Information Technology and Society, a founding faculty member of the Media Arts Technology Program and Technology Management Program, and the Computer Engineering Program. He is the author of many papers in scientific journal. He serves or has served on many steering committees, bodies. He's very active in the IEEE and the ACM and the IETF. I first came across Kevin Almaroth when he was the chair of the Internet 2 working group on multicast, and that's actually also the topic that he is going to speak about today. For me, as a completely non-technical person, I always have a very simplified version of things to remember, and what I remember most recently about multicast is a message like, it was a good idea at the time, but it doesn't really work. Now, I understood from Kevin Almaroth's abstract that that is not his view at all, and that's why I'm very curious to hear what he's going to tell us about multicast. Kevin Almaroth.
All right, thank you very much. Well, I'm not exactly sure that I'm going to say that multicast works. In fact, I'll go ahead and skip over the preliminary introduction and just go to the first slide. I think this sort of sums up what a lot of people have thought about multicast for a long time. Essentially that it's the poster child for the irrelevance of the academic community. That there are a few other technologies that have generated so many research papers while yielding so little real-world deployment. And this was SIGCOMM this year from ACM SIGCOMM. They've done public reviews of some of the accepted papers, and so this was one of them. And in accepting this paper, they felt that the strength of it was sort of trying to understand what went wrong with multicast and to provide an alternate solution. And that really is the theme of my talk today, especially sort of given the group and the theme of the conference itself, and given that there's a fair balance between network operators as well as researchers and academics. So we all sort of approach multicast from a different perspective, and that's really what I want to talk about today. This would have been a good talk to do as a panel, so what I'll try and do is present both sides of the story a little bit. So obviously from this side, there's clearly challenges that multicast had and that it continues to have. And so I also want to present some of the strengths and where I think we'll be going in the future. So you have this slide. Clearly, I think there's been a lot of understanding, or at least a discussion about what's happened with multicast. And one of the things that I wanted to do was look a little bit at the failure of multicast and sort of why it's happened, especially to ask a broader question. So I'll come back to this question at the very end, which is, if we want to continue to evolve the Internet, how are we going to be able to make that happen? Aside from the failures, the technical failures of multicast, what are the things that we can do to get new services deployed in the Internet? So I've spent about 15 years working on multicast, probably only a couple of years removed from the very first experiments in the M-bone. And one of the research topics I've been focused on is to look at how multicast is deployed, its growth in the Internet, how it's used. And so we've collected a fair amount of data. So the slide that I want to show you that sort of quantifies multicast failure is really to look at the amount of multicast that there is in the Internet. And really the way that we use to measure this is to look at the number of BGP prefixes that are specifically for multicast. So as the slide says, when you're interested in joining a multicast group and you want to reach a particular source, you follow a path back to that source. And when you do that, before you do that, there has to be an advertisement on how to reach that source. So that comes through in BGP. So the metrics on this next slide really look at the address space, the number of prefixes, and then also the ASs as an estimate. And we consider this based on unicast to normalize it, because obviously there's been an increase in unicast. I could put a positive spin on this and show you just multicast prefixes and show how it's grown, but when you combine that with how unicast has grown, what you'll see is that there really hasn't been a lot of growth in multicast. So, in fact, this graph shows in fairly depressing version that there's been fairly little additional deployment. So where we stand now is about 10 to 15% of the Internet is really multicast capable. And so from that perspective, largely we can say that multicast has been a failure from the goal of trying to deploy this as a ubiquitous service. The question then is, what is it that we really set out to accomplish? Or what is the thing that we wanted to do with multicast to really make it a success? So what I tried to do is come up with a succinct statement that throws everything into the mix that we possibly could have wanted for multicast, and then we can start to look at why it's failed from those issues. So we wanted it to be ubiquitously deployed. We wanted to be able to join a group no matter where we were, no matter where the source was, and to have it work. Obviously, we wanted it to be revenue generating, especially for the ISPs who were expecting to deploy it. Native, one-to-one, or one-to-many, both many-to-many, and then all the kinds of applications that we envisioned. So from all the kinds of streaming media to TCP-friendly file transfers, one-to-many delivery of content, audio and video conferencing, minimizing delay and jitter, potentially involving some QoS. And we wanted to do it with a minimal amount of additional complexity. So it wouldn't be hard to deploy, there wouldn't be a lot of overhead, there wouldn't be a lot of state, there wouldn't be a lot of security weaknesses, it'd be easy to use. And this was sort of the vision for multicast once it sort of got into the mainstream IETF. And I think that this was a little bit overzealous, and this is probably what people use as the metric for deployment. Well, I tried multicast and it didn't work. So in that case, it essentially has failed. There's plenty of results that show that it's not widely deployed. So I think we can tie a bow on it, say that it's done, and move on to some new research topic. From that perspective, there certainly then are lessons that we can learn about why multicast is perceived to have failed, what the things are that we can do to make it better, if we can salvage multicast at all, essentially how to try and make it work. So the question then is multicast really a failure, especially given sort of the summary of the things that I've presented in the last couple of slides. So then on the other side, you might have somebody on a panel, or I'll sort of turn this way and say that in a certain sense, multicast has been a tremendous success. And the real success of multicast is not in its visibility as this inter-domain, public, ubiquitous kind of service, but for a variety of applications inside of particular domains. It's certainly the case that for services like multicast, it really isn't designed to be used by every single user in the internet. And I think we're going to continue to learn that about services today. So for example, if we want to talk about dedicated or dynamic light paths, is that the kind of thing that every person would want? Very likely not. Is it the case that everybody is going to want some kind of QoS? Again, very likely not. So as we think about the kinds of services, we certainly initially envision them as being fully ubiquitous and deployed and accessible by everyone. But it really is a question of who's going to use these services, for the benefit of whom, and how are we going to make it technically possible. So from that perspective, there certainly is a lot of information or a lot of case studies and a lot of situations in which multicast has been successful. Certainly in the kinds of networks that are represented by the attendees here, within Internet 2, within gigapops, within regional networks, when there's an attention towards research, multicast is one of the services that people try and look at. Now, of course, in a lot of cases, it's a novel, it's interesting, it's cool, it's sort of geeky. Let's try it and see how it works, and then spin it up and run applications on top of it. So, it might be the case that this group is a little bit biased in saying, sure, I'd be interested in multicast. The counterpoint to that, then, is how often is it used? So it's certainly the case that campuses and regions have spun up multicast only to find that people haven't necessarily used it, that the researchers or the people who are really using the high-speed networks haven't turned to multicast as a solution necessarily. And that's certainly a problem relevant to multicast, this chicken and egg problem I'll talk a little bit about. There are enterprises. So, for example, this is not public companies, but companies that are running their own internal networks. The Ciscos and Microsofts and Intels and BTs of the world spend a lot of time using multicast. They produce a tremendous number of applications that stream audio and video or do content delivery, all within the confines of their network. So they're not going to advertise multicast reachability to the outside world. It won't be the case that you'll see a streaming event that happens on the internet and receive a lot of publicity. Yet these networks and these companies have used multicast to tremendous success. Another area where it's been successful is in stock exchange companies. They use this to stream information, both quotes and transactions. And they have very robust infrastructures for providing multicast. Other kinds of edge networks that we call walled gardens. It certainly is the case that the internet is evolving so that it's not completely homogeneous, it's not end-to-end, it's not completely open any longer. And within some of these networks, there also is a lot of multicast. In particular, companies that produce triple play equipment. So if you're going to do voice, video, and data over a cable network, often cases the video is provided using IP multicast, or at least a variant thereof. And then, of course, there's the military network. That's probably all I'll ever say about the military in this talk. But certainly there are people who spend lots of money on networks, and multicast is a driving service, and some of the applications based on multicast are as well. And sort of to think back to that original slide about academic research, if you think about where multicast originated, so Steve Deering's PhD dissertation at Stanford, the whole idea of how to deploy multicast in the internet came from academia, was incubated in the IETF. The vendors were heavily involved. There's tons of startups that have come about, products from companies. It's people's jobs to engineer multicast, content providers. I'm sure there's certainly other services within the internet that have generated equal amounts or probably even greater amount of interest. But one of the interesting things about multicast is that contrary to what some people will say, and if you stop and think about it, multicast has been a tremendous success. So again, the two sides of the coin, multicast is really considered a failure in terms of a mainstream service, but there are benefits to multicast, and there is a lot of it deployed throughout the internet. So, to try and broaden this talk beyond multicast, especially for everybody who is happy to get up at 9 a.m. and be here for this talk, there is a lot to be said about other services in the internet. So you could almost do a global search and replace of the word multicast with things like IPv6 or with quality of service. Again, there's been tremendous amounts of interest in the academic community. They've sat in their ivory towers, or shall I say, we've sat in our ivory towers publishing papers on this. and not necessarily having an effect on the mainstream. And the question then is, are these services really going to be deployed in the internet? Certainly there are differences between these in levels of deployment, but certainly it's also the case that there's a lot of similarity. And then, of course, maybe ad hoc networks fits into this category as well. I haven't really seen an ad hoc network, but soon, maybe. Okay. So given that second slide and this disconnect in the perception of multicast, and certainly the common idea that multicast has been a failure, the real question is, why is there this disconnect? And why is it the case that engineers who work on multicast networks consider it effective and successful, but the mainstream considers multicast not to be that successful? And I think one of the trends that I've observed is that multicast sort of evolved at the same time that it was being developed. And this really caused some pretty serious problems. So it wasn't too long after the idea was proposed that you had prototypes, you had the multicast backbone, you had the vendors at the IETFs talking to people and saying, well, we need to change this. So you'd get some of the vendors, they'd log on to their core backbone routers, they'd change code, they'd re-upload it essentially on the fly, and essentially change multicast in its operations without really thinking a little bit longer term about what those implications would have. Certainly it's the case in any source multicast versus single source multicast that finally when we said, eureka, we need to take some of the complexity out of the network, that there was a little bit of apathy about trying to deploy yet another kind of multicast. The vendors were sort of tired of implementing and changing protocols. The switch vendors didn't know whether to implement IGMP version 2 or version 3, or maybe there's a version 3 Lite. So the protocol soup associated with multicast was really happening in real time in the way that the service was developed. And I think it's created a certain amount of apathy and a lack of confidence that there really is an architecture that we can use to provide. Even today when the folks who support SSM say, SSM is really the way to go, there's still a little bit of a challenge in getting the vendors and the content providers and everyone else involved. And then, of course, there's that second point that at some point, trying to get the infrastructure to change is really difficult. Even the vendors become hesitant to implement a new version of multicast simply because they've got lots of deployed multicast already. And if they make a change to the infrastructure or the architecture, then you have this disconnect between deployed services. So those become real problems as well. Certainly I can criticize myself as an academic. There's been a tremendous lack of discipline. We've started up multicast communities in academia that have started workshops and conferences, and we really allowed papers to be published which had no tie to reality, that there are assumptions about the way that the internet works which aren't true. There are assumptions about the way that we might deploy these services or the overhead. And it really is the case that we've deployed or allowed to be published these system after system after system that proposes a brand new kind of multicast routing that's never going to see the light of day. And given then that there are all of these papers that are sort of disconnected with reality, there's this perception that there's this tremendous body of literature that we should be using to change how multicast is deployed. And that's certainly not the case, that there is a disconnect between what we talk about in academia and how we would want to engineer the network. And then also in that second long slide filled with lots of text where I talked about all of the things we expected from multicast. We expected it to do everything, to have all of the magic already mixed in, to do authorization and authentication and TCP and friendly and congestion control and reliability, everything mixed in there together. So there was a certain set of expectations that were never really able to be met for multicast. And that really creates a problem, that if you expect multicast to be ubiquitously deployed and it's not, then it's pretty easy to call it a failure. Okay, so speaking of the groups that are involved, it really is an interconnected community. So if we think about all of the people who are involved in multicast and what has to happen, and again, you can replace multicast with any other service, but there's a tremendous amount of cooperation that really does have to take place. If there's any group represented on this page that probably doesn't care, it's likely the users. They just want to be able to start an application and receive content, and if they open an application and nothing shows up, then it better not be that there's it's because nothing's being transmitted. It better be because nothing's being transmitted. It better not be because there's a fault in the network somewhere and nobody can track it. So if you think about the relationship between all of these different groups, it's understandable why deploying one of these services is hard. And again, because multicast is assumed to be end-to-end. If there's any hop in the path that doesn't understand a Class D IP address and doesn't understand what to do with a join, then the whole end-to-end path is broken. And that's a problem, for example, that doesn't really exist in IPv6. You can do tunneling, you can do encapsulation. So this assumption that you would need all of these pieces is something we should have had some foresight about in the beginning and said, well, we really ought to be careful about what we want to be able to say about multicast. Okay. So it's not just one chicken and egg, it's a whole farm of chickens and it's a whole omelet of eggs mixed together, that all of these things start to become dependent on each other. We're not going to have any applications until we have an infrastructure that works. We're not going to have an infrastructure that works that people want to support until there's actual interesting content. So all of these things are interrelated, and trying to figure out which one to tackle first is the real challenge. Okay, so to focus a little bit on some of the problems and experiences that we had in the Internet early on, I'll just pick on some of the big problems with multicast. So there's really two that I want to focus on in a little bit more detail, the ones that I hear coming up most often. The first is that the service just didn't work. Multicast was really first attempted in about 1992. It was all done with tunnels and overlay. It was called the M-Bone. You had a few sites set up relay nodes. It was really an interesting experiment that was designed not particularly to scale, but to demonstrate the power of one-to-many communication. To build a service based on that is a real challenge. And so the major difficulty that we had was how to turn that into that service that it was actually going to work. So it was very often the case that it didn't work. And this goes back to the point that if you're trying to develop the next generation of protocols for multicast while you've got a deployed infrastructure, it makes it very difficult to run accurately. And the same thing happens for all of these supposed research and education networks where we're supposed to be prototyping the next generation of protocols, where very quickly they turn into production networks that if they ever go down, users get upset. So there's this real trade-off between whether you want to make something production and functioning and whether you have the ability to test it and make changes and experiment. And then there was a little consideration for large-scale deployment, what it would mean to extend beyond one of these test networks. And again, it would really be the IETF's responsibility in standardizing these protocols to make sure that there are issues that are dealt with in the community. So for example, if you've got an ISP and you're asking it to deploy multicast, what are the advantages? What are the economic incentives that have to take place before that happens? Now, the IETF would like to think that it doesn't have a role in considering economics in standardizing a protocol. And that's certainly the case, but when it comes to a working group that's focused on deployment, understanding the economics certainly does help, especially when you're trying to improve the deployment. So a little bit more about each one of these. So I'll flip back and be my cynic about multicast again, that it was essentially doomed from the start. So what Deering's dissertation really was about was land-based multicast and how to build a really fast distributed system using one-to-many communication on the LAN. It was never really designed to be intra-domain, let alone inter-domain, let alone support the variety of applications that were initially assumed. In fact, while Deering's dissertation originally talked about doing data dissemination, file transfer, one-to-many, the big application from early on that everyone seemed to seize on was audio and video conferencing. And it even wasn't until later when we started to think about just one-to-many content delivery, near video on demand or some sort of broadcast. So it was hard to get away from some of those initial assumptions, and some of those still exist in what we do with the infrastructure today. Probably the biggest one has to do with accounting. That in order to make it scalable, you don't want the source to know who all of the receivers are. Well, if you're trying to do accounting, that's one of the things you really look to multicast for. So the first step then beyond Steve's dissertation was a small one, and it worked fairly well. For the M-Bone, as long as it scaled, the number of mRouteDs that existed, even when there was initial native support in routers, the MBOND worked fairly well. There weren't too many problems with it. But to try and get it to scale beyond that small experiment was really difficult. Now, at the same time, the research community only would consider options that were infinitely scalable. If you tried to introduce any kind of reliability that caused some sort of perceivable collapse in scalability, that you might have to send acknowledgments from each receiver and that would cause an ACK implosion, people would get very upset. It was only the case that you could propose a multicast routing algorithm that seemed to scale beyond the horizon. In fact, there was a paper in SIGCOMM fairly early that talked about just using the destination or using the IP options field and just packing some more destinations in there. And then when a packet got to a router, the router would look at all of the destinations, and if it had to split the packet at that point and divided up the set of destinations into 2 or even more outgoing interfaces, then it could do that. But that was dismissed because you can only pack so many IP addresses into the IP header, so it's not really scalable. This is really an idea that's also starting to come back a little bit. With a fairly small amount of implementation, you can do one to a small number of destinations without having any per flow state. So the other problem is that what was deployed didn't work, and there were really a lot of problems for why this happened. So as we tried to scale and as you started to see routing misconfigurations or router misconfigurations, as you started to see bugs in the routers, as I said, it wasn't uncommon that at an early IETF meeting, some of the principals from some of the major vendors would sit around in a circle and say, hey, here's a bug, let's fix it. They generate a new version of the operating system, recompile it, and throw it on some of the routers to test it, and in the same time introducing some brand new bugs. So it was very much a loose prototype kind of network, and as a user, you didn't really expect that to influence your experience. So if it didn't work, it was very often the case that you wouldn't try it again. There was enough of a learning curve to get started. You had to download the applications, and if they simply didn't work and you didn't know why, you really just never came back. So trying to build a strong and heterogeneous user base early on turned out to be fairly problematic. And then, of course, this major problem that really is dealt with in conferences like this fairly often, which is how do you bridge the gap between the users and the network? Do you ever give users access to what's happening in the network so that they can see and that they can develop their own debugging information and potentially report that to a network administrator? Or do you make that demarcation point very strong where the network is truly opaque and the users can't see into the network at all? And so we've gone around in circles with this in multicast. What's worse is even for the network operators, multicast looks fairly opaque. And so we continue to develop even the most rudimentary tools today for how to try and debug multicast. Now, given that there's been a lot of attention in that fairly recently, at least we're making making some progress. So 2 experiments that I wanted to talk about and that I wanted to show a little bit. One is this, it's a little bit fuzzy, but what you really want to get is you want to get that there are some blocks that are dark and some that are light. And what we did was we collected all of the sessions from the session directory, so those are the rows, top to bottom, and we collected all of the session directory information from lots of different users. Now, one of the things that you might expect is that really this whole thing should not be red, right? Or there shouldn't be dark blocks in here because everybody should be able to see everybody else. This is also for all the global sessions. Now, certainly it might be the case that a whole row might be red, which means an advertisement isn't seen by anybody. Okay, well, that's probably because there's a local problem or something like that. Or a whole column might be red. And that's the case where somebody's running a session directory on a network that doesn't support multicast. Okay, fine. What really is intriguing is after you run this for a fairly long amount of time and collect data, there are places in the network that just don't see other sites. So you really have a discontinuity in what the routing infrastructure looks like. And these problems persisted for long periods of time. So there's this kind of view, which is what the users see, and then there's also this kind of view for what the routers see. So what the left graph shows you is sort of a fully connected multicast architecture with all of the BGP paths being shown. And then each one of the panels shows you what individual routers might see. And clearly this is a pretty extreme example, but it's the case that some networks only see very limited numbers of other networks. Now, you could say, well, this is probably because of BGP policy, and it's not the case that I should see everyone else, that if I route to somebody. But for multicast, the policies for multicast, the BGP policies for multicast are fairly liberal and continue to be. So it's not often the case, or especially early in the days of multicast, that you should have this kind of disconnected topology. So for the whole variety of reasons I mentioned earlier, multicast went through about a 10-year span from about 95 to even a couple of years ago, where there were significant disconnections in the infrastructure. And this goes back to the exact same problem. If you try and join a video conferencing session and it doesn't work, and you know that the tools work, what do? You blame the network. Well, the network's opaque. You call up your network administrator, and it's not always the case that they even know what multicast is. So there really is a challenge in making sure that the network is robust, that the infrastructure does stay connected. And I think that's a problem that's being solved slowly over time. What we then have to do is deal with the black eye that multicast has received. Okay. There's also a question of deployment related to economics. And this is really sort of intriguing, and it's also not the case that many people have thought about multicast unless there's really been a consideration for how to deploy it. So I go back to sort of some of the groups that are relevant here, and the first one is the users. And the users really don't care how they get the content. In fact, they'd really prefer to get the content without having to worry about whether it's multicast or not. So they're sort of out of the equation. The ISPs who do the bulk of the deployment are really in the unique position. They never really figured out how to charge for multicast, right? There's this perception that, okay, if I only have to receive one stream from a content provider, then it gets distributed through the network, so that should reduce the amount of traffic, especially considering if the users, or if I'm doing this by unicast. So on the one hand, the ISPs know that they're carrying less traffic. At the same time, they often charge on the amount of traffic that they're able to carry. So really, there's only a small sweet spot for multicast for an ISP's perspective from a charging point of view. If their network capacity is completely consumed and they're charging everyone, the only way that multicast makes sense is if they can then deploy multicast, reduce the total amount of traffic through their network, but still be able to make the same amount of money. So then you come up with really weird kinds of charging algorithms that are independent of what multicast is trying to do. So UUNet, for example, had a service called UUcast that charged people based on the number of receivers that there were. But everybody knows that the way that multicast works, especially for content providers, you give them one stream, and then they may or may not have to replicate it. So, those kinds of models never really made sense. And when the customers didn't buy into them, neither did the ISPs. So there is a lot of economics for how you try and get a service like this deployed. And then, of course, the content providers loved it. And then the application developers were a little bit stuck because they didn't know if they were going to run on a network that supported multicast or not. So the challenge of economics, I think, was one of the things that really caught multicast and discouraged its deployment, especially in the commercial sector. So in the research and education networks, you don't have this kind of economic problem. Clearly, it's a free-for-all. Go ahead and deploy it and see how it works. So there were a litany of other problems just to sort of throw more fuel on the fire. I'm not really going to go through much of these, except for maybe the last one. I mentioned this as one of the major problems. And it's also an area that's probably received the most amount of attention. So how do we understand what's happening with multicast, and how do we try and debug it? I think the other big issue that worries network operators is the fact that multicast traffic is all UDP. And it's hard to constrain UDP traffic. And they say, well, how do I manage multicast traffic? Well, it's the same way you normally deal with UDP traffic. Well, how do they normally deal with UDP traffic? Well, they probably just block all of it, especially for really paranoid ISPs. So, multicast has an issue of, per flow state and then how to try and manage it. So those are sort of some of the common problems that still exist. So, in terms of current adjustments, one of the things that I haven't done is to list some of the adjustments to the problems listed on the previous page, but certainly there's a lot of work going into how to solve those problems, how to solve monitoring problems. But I think one of the one that's really worth talking about a little bit more is some of the work that's still going on in the IETF now. There's the Internet Research Task Force, which is different than the IETF. And there's a research group on scalable adaptive multicast. And they've got a mission statement, and it's fairly good in terms of what they're trying to do. So the main thing that they're trying to do is work towards a hybrid solution to try and find a solution that bypasses some of these bottlenecks. In particular, they're looking at a solution called AMT. Now, I haven't talked a lot about application layer multicast and how it essentially is going to work or how it fits into this. But it does have a role, and it does fit into the architecture. So we're going to continue to work towards a hybrid solution. There is a role for application layer multicast and tunneling inside the infrastructure. And so the question then is how to get the academic community re-engaged. And so there are conferences and workshops that we have to establish, and then try and also get the funding agencies more involved to try and support multicast, because there are problems that can't be provided through engineering and through deployment alone. Okay. So real briefly about automatic multicast tunneling. Essentially what it allows you to do is to be able to support multicast in an application even though you're receive only. So let me sort of just continue through. Essentially what's going to happen is when you send a multicast join and it reaches a router that doesn't understand what to do with the join, it's going to encapsulate that join and send it through the network. And what the network is then going to do is route that request until it reaches a router that does support multicast. And then from that router back to the receiver, you'll be able to... So, hold on, take another breath. So you'll be able to route back to that receiver using unicast. So in that case, that's the TAN line. Okay, so I've only got 2 more slides. I should be able to get through this. If you have a lot of unicast receivers who are interested in receiving this tunnel or receiving this content, now you have an incentive to deploy multicast. Okay, so I'll go ahead and finish up. That there really is an interest in continuing to deploy multicast. So, and that's it. So.
Would you like a chair?
So,
Get the shit down.
You can sit down.
so I can answer questions.
Okay.
Any questions?
Case has a question.
It's also a ploy not to have to answer questions. Okay, can you understand me? Absolutely.
You know that this is not now it is working. You know that there are also other developments in distributing video, like BitTorrent kind of protocols or peer-to-peer protocols for distributing video and even streaming television material. I think BBC is doing that, or somewhere I've read about such an experiment. How do these peer-to-peer and BitTorrent distribution methods compare to multicast, and could that ultimately be more the future than multicast?
Is there a microphone? Okay, so with peer-to-peer, so that's a good point. Originally, we thought that peer-to-peer applications would supplant the need for multicast. And essentially, there is a role for peer-to-peer in relay. The real question is it going to replace the need for multicast? And the answer is very likely not. Again, if you go back to different classes of users, there are certainly the college students who want to do peer-to-peer deployment. They're willing to wait essentially forever. But there are also classes of applications where you do want to do high-quality content delivery where there is potentially a need for multicast. Now, it's also the case then, if you go back, can you go back essentially, yeah, to right there. So this is an early picture of the M-bone. It's about 1994. Multicast was deployed originally using tunnels. So there is the potential to do relay kinds of infrastructure. You certainly could do multicast within a BitTorrent kind of environment, especially if you have a reliability mechanism like, say, a digital fountain. You could use multicast in peer-to-peer. So it isn't that the two are orthogonal or that they can't be used together at some point. I think there's a bigger picture in terms of what peer-to-peer clients can even do. So, for example, look at the power that peer-to-peer traffic has caused for network operators. So we never predicted this application, and it's had a tremendous impact on how we run our networks. So, yeah.
Okay, thank you.
Other questions?
Any other questions?
No sympathy. Somebody go for it.
One of the issues of multicast has been in deploying TV over IP as a capability for user to zap from one channel to another one.
Right.
What is your answer when a provider has to stream around 300 channels, which is roughly the target they have today, in order to make the user experience acceptable, which means probably less than 1 second to switch from one channel to another one?
Right. So this is a problem that the triple play networks have had to try and solve, and it's not so much the join latency that's the major issue. That's fairly small, especially in a network where you've only got a few hops to the content source. So, for example, in an IPTV network, the join latencies are less than 100 milliseconds, so that's not so bad. The major problem then is the leave latency. And so often cases, what you do in the last mile is instead of this sort of one bit for whether there's any receivers downstream or that there aren't any receivers, now you keep track of receivers on a per receiver basis. So it increases your state requirements, but when you have the last user leave, then you really know that that user is left. So there's a way of solving the leave latency issue, which makes sort of multicast as an IPTV solution something that's actually workable. So, sure, there's a question here.
There's a question over there.
Camilo Zaccone from the AWT. So in the same trend as the two previous questions, where one was talking about the peer-to-peer technologies and protocols, and the other one talking about the video streaming technologies to have IPTVs, don't you think that if we have opportunities like nowadays Juiced, which is in fact combining peer-to-peer to provide IPTV, and in a certain sense the marketing that they have on the behind and the full sets of actual users they have might supplant deployment of multicast, because we heard about multicast for years. We know that it's there. We know that there is a potential, but it's still R&D-like technology. Right. So I want to have your opinion on this subject.
So there certainly is a concern of whether sort of basic peer-to-peer will supplant multicast. I think it is very analogous to the argument of whether NAT supplants the need for IPv6. And I think in the end that there are a certain number of limitations to what peer-to-peer can do. So, for example, peer-to-peer isn't scalable by the definition of scalable. So the real definition of scalable is that you can service additional users for an incremental amount of additional cost. And where you get your savings in peer-to-peer is really through load distribution. So it isn't the case that peer-to-peer replaces multicast. It might accomplish similar functions, but then this is back to where you have applications that really demand on the performance and you can't rely on peers necessarily. I think it has the same kind of comparison to IPv6 and NAT, that certainly it sounds like you could supplant it, but in the end, probably not.
Okay, the last question is from Marco Samani.
Yes, I agree with you about the fact that peer-to-peer does not scale, but I want to observe that peer-to-peer teaches us that users want to be content providers, and I think this is something that is under-evaluated very much. It is true that as long as the user is a receiver, he does not care about multicast, but when he wants to be a content provider, this would change immediately. But I see that very few people, both among the providers community or application developer community, under-evaluate this point. So what's your opinion?
Right. So I think your question points to the fact that there is a tremendous amount of interest in peer-to-peer, largely because there is so much traffic. I would likely argue again that multicast isn't supplanted by peer-to-peer. You really mentioned that users have their own content that they want to publish. That's certainly the case, but what you're asking them to do in a peer-to-peer network is relay. You want them to relay other people's content. And then it becomes a question of incentives again. So, I always thought an interesting application would be when we get to the point where the people who own movies are okay with distributing those movies over peer-to-peer, then you go, and this has been discussed, that you encrypt all of the content, and then you pay for a key to decrypt that content. And anybody who helped deliver that content to you, because you would do it in a peer-to-peer fashion, would receive some incentive to do that, some fraction of what you paid for your key, for example. So again, peer-to-peer really is an effective strategy for distributing content, and certainly, it has been what's become common. And in the same way that peer-to-peer doesn't require deployment of infrastructure inside of the network, that's really been the major detraction of multicast. So I think everyone's perception about the role of multicast and its limitations, especially relevant to the peer-to-peer revolution, really are very much true. I would still argue that there's a role in maybe in 10 to 20 years in certain kinds of applications, they really only will be doable with multicast.
Okay. Thank you very much.
So,
let's give another big hand for our speaker. Started. Okay, let me introduce our next speaker. I refer to John Murai as the grand man of the internet in Japan. He has many functions, has done many things. He is currently vice president of Keio University and a professor of the Faculty of Environmental Information there. Best known to many of us probably as the general chairperson of the White Project. He studied at Keio University, got his bachelor's, his master's, and his PhD there. As I said, since 1997, he's a professor at that university and a vice president since May 2005. Between 1999 and 2005, he was executive director of the Keio University Institute. He has had many functions, as I said. He has been the program chair of many conferences. He served on the IAB from 1993 till 1995. He was a trustee of the Internet Society from 1997 till 2000. He was a director of ICANN from 1998 till 2003, etc., etc., etc. He is one of these persons who can speak about the technology and the applications and the governance of the internet, about the present, the past, and the future. And I think it's about the future that he's going to talk today. Yun Murai.
Okay, thank you very much for a very nice introduction. I'm very happy to come back to Terena. Last time I was here was probably 2000, year 2000. I was with a band, and we talked about the internet is for everyone. Now, internet is for everything, everywhere. And so there are certainly new requirements coming in. And so it's a very, I feel a lot of excitement to and challenges for the new requirements. And multicast is certainly one of my favorite topics. And probably therefore, this session was, kind of constructed. And so I'm also a big fan of IP version 6. And so anyway, so the WIDE project has been, actually celebrating, we'll be celebrating its 20th anniversary. It's amazing. We've been doing for the networking researches and everything, but the WIDE stands for Widely Integrated Distributed Environment. So we kind of started to believe that the entire world is going to be a single distributed system, and then how we can manage that. And then the networking protocol was one of the areas that we had to challenge. And we've been working for the IP version 6 and other things. And also I came from Tokyo this time, and traveling to Delhi, Cambodia to work for the Asian networking thing. So the requirements is coming from the Asian region, new requirements sometimes. And then so this morning I'd like to share with all of you here about what kind of new requirements I feel, and what kind of solution we are challenging as a WIDE project at this point. And that's the purpose. And then I came from Tokyo, meaning Japan. And then you are European community. You named us Far East. So this is a map, also generated from the various networking community. You call us Far East. Where is the East on this map? So from a networking traffic-wise, we are Far West, right? And look at this. This is the year 2001 traffic of the internet. This is 2005 of the internet. This is telecommunication in general. So all of the picture telling us that our world is connected, starting from Japan, Asia, and then ending at basically Europe. So that's a world map we are looking at. So don't call us so Far East anymore. You started to call us. And anyway, so let me start with a kind of a background information. We recently did with all of the major ISPs in Japan. And this is a traffic analysis program, which has been, known, very well known that it's a very hard work. But finally we did that. And then some of the results already shown in the SIGCOM, and then will be shown in the next SIGCOM. By the way, the next SIGCOM would be in Kyoto in this summer, so please come. What we were kind of focusing at is, Japan is well known as a broadband to home things, and a very inexpensive broadband channel. And so this is basically telling you that the 10 gigabps or multi 10 gigabps of a light path fiber, that kind of things is only within the R&D network, scientific research computing community. And then, since a lot of broadband home users in Japan starting to utilize a lot of multicast, video streaming, and other things, as well as file sharing P2P. So analyzing that kind of thing from a traffic point of view, working together with the major ISPs, that's basically what we've done. And some of the results is in here. Some of the results you can consult to the Silicon papers and also the Silicon workshop coming in the summer. So basically this graph is a FTTH, fiber to the home thing, and the green one. So hitting to 10 million subscribers to the fiber to the home thing in this year. So then this is ADSL. So ADSL is a kind of stop growing thing. So the fiber is going to be connecting to, kind of most of the homes, I should say, and as well as enterprises and everything. So so far they are using the 101 gig, but they can, by the lower cost of the equipments and probably they can, they can turn out to be a 10 gigabps and others. So some of the DSL users, FTTH users, and how the traffic is consumed. And basically these graphs, we wanted to check that if your home is connected by a fiber, you have a 1 gigabps connectivity, 10 gigabps connectivity at home, what purpose are you going to use? And then, so everyone said, oh, that's a P2P, and you're going to serve for the community. And you have a lot of files, and then, you can get the others downloading from your machine. If that is true, then, the traffic might be a kind of a flat. And this is a weekly traffic you are seeing. So it's a kind of everyday, Monday, Tuesday, Wednesday traffic. So it's active at night and then disactive during daytime. So this is a normal pattern for the traffic of the users when the human being is actually using it. So this is the constant part might be the P2P file sharing type of traffic, but this is actually the human being active, activation of the traffic things. So basically, that kind of a traffic analysis, we've been doing that, and then find out that this is, by the way, the top 10 heavy users of the traffic patterns of the week, and then why we wanted to check that, and then we wanted to make sure that the variety of usage exists. Is a heavy users. So basically, this is showing the enough variety from us, and so basically, we are expecting we are believing that that every single person at home is going to start generating a lot of traffic in many ways, and then we can. This is an inbound and outbound from home to home type of things, and then fiber to the home people traffic is tend to be a kind of connecting, and then outbound is growing faster. So this is basically remote storage application type of things, and then pushing the data out from home to secure your data, that kind of thing. So anyway, so this type of very interesting behavior of the human being at home using the digital network things, it's having monitors. This is a good thing. So this is basically the background of my talk this morning about what kind of new requirements is coming in for. So basically, the 10 Gbps fiber user is not only for the R&D anymore. So variety of usage is going to be existing. So if you are discussing more about this, then you can come to a Silicon. By the way, Kenjiro Cho is a person who's been in charge of this traffic management, traffic analysis project. So anyway, so the first requirements and the first things the WIDE project has been very much interested in is the unwired internet. So the internet has been with the fiber and the cables, but now it's with radio wave and other things. But IP over wireless is a very interesting thing. I mean, cell phone, mobile device, Wi-Fi. But we are kind of trying to do more on this. So the digital broadcasting TV is going to be starting. It's already starting, but we're gonna stop the analog TV system in the year 2011 in Japan. And after that, who's going to use that frequency? How we're going to use that frequency after that? I mean, analog TV frequencies we are using at this point. And the WIDE project has been testing the IP over broadcasting media using the TV signal things. So this is basically what we've been working. WIDE project has been working with the European people called the unidirectional link routing things. So using the broadcast media, passing the IP to the many nodes, and then coming back with the tunneling back to the source. That's basically the concept of then pretending and creating the illusion that the broadcast path being the bidirectional path for the internet. So that's basically the UDL, how the unidirectional link routing works. And we are still working on it, and we are using it. So therefore, when we basically the concept is like this, and then we are cable, to the home and everywhere, and in the air we have although it's not visible, but we have a cell phone packet type of things in the room. And then when you go out, then we can receive the signal from the air or from the satellite or whatever. And all of them are carrying the digital signal now. And then how are you going to produce the entire thing? So that's basically the purpose of the IP. So the telephone company, cell phone company is talking about the all IP solution. And then, that's probably the things talking about. I mean, before the TV signal broadcasting radio wave, and the other things, Wi-Fi and the cell phone cable are kind of independent networks. And then, of course, interconnection among them could be achieved by the internet sometimes. But then, what we are not talking about the business, but we are trying to do, as a WIDE project, as a research entity, we are trying to achieve that everything, every possible digital media using the IP layer transparent to the other upper layer protocols, so that the space of the living space and the environment that would be kind of filled with IP possible paths. But the point is that our engineering power sophisticated enough to produce that kind of thing, monitor things. Our routing technology, for example, is sophisticated enough? That's basically the question. So what we are doing, we are kind of having the capacity of the satellite bandwidth, and then doing the broadcast, IP over broadcast things to entire Asia. And then the routing is going to be, the multicast packet going to be routed to the satellite station, so that basically the working as a normal internet routing, but it's try to be more sophisticated to maximizing the usage and the efficiency of the underlying path. So that's basically the things. One of the thing is that we do have a satellite capacity, and then allocating the frequencies dynamically. So this is a special agreement with the satellite company. And so using the biggest portion of the frequency for the IP over unidirectional routing things. So unidirectionally passing the IP signal from the sender. And then all the Asian universities, currently up to 24 universities are receiving that IP signal. And then a return path is going to be a tunneling back to the originator of the traffic. So that's basically the portion. And then if the traffic grows, then we are dynamically allocating the more frequencies and by kind of shrinking the bidirectional use of the other satellite part. So this is basically covering the entire Asia. So using this is IPv6 only multicast over the broadcast channel, so seamlessly connecting with the normal IP routing things, so that basically this is as an application we are using the distance education, university class sharing things with the installation and the operation is going to be by the student researchers themselves, and all the countries like Cambodia. We are having the meeting right after this in Cambodia, collecting all of them. But then they are very much the kind of people who's going to be operating for the next generation of the information infrastructure of each of the countries. So training workshop for the entire week, twice a year type of things. And then they are all speaking the IP version 6, by the way. So probably the IP version 6 speaker is large in here and Asia. Sorry. So probably we are speaking the same language. So the distance education management operation and then the networking operation is going to be done. And so that's basically the wireless, unwired internet, connecting to the wired internet, and then using especially focusing on a broadcast media, use of the broadcast media, and then nothing is going to be an exception. So every media who's passing the digital data, then I really want to see under the internet protocol. So that's basically the way of what project is working on. And so the speed is growing, and the network speed is growing. This is one of the graphs Professor Hiraki of University of Tokyo mentioned, and then both each of the network equipments. I mean, growth of the speed is like this kind of line, and so we're expecting. So we should be expecting for the along this line, and then higher speed of technology is going to be coming up. And then this is talking about the computer things, and then the computer speed is kind of getting faster and faster as a kind of a same manner. And we do have a kind of way to project the future of the speed for both of the network and the computer thing. So they're working together with Professor Hiraki and the White Project, and then we are kind of trying to create the single fastest computer with the shape of the Earth, and connecting each of the elements is going to be distributed around the world. And then the sophisticated protocol is going to be kind of inside that kind of distributed computer things, and then kind of challenging for the fastest computer in the world. So the new type of a supercomputer type thing. It's very similar to GRID, but we are also working and doing research of each of the elements from the very much basic things, and the global computer networking things, and then the long distance TCP control, and so the processors, chip design, and that kind of things working together for this is basically from the academics research areas, but we do have a testing or the practical testing using the R&D network. And then, so creating that kind of distance and the fat pipe, TCP control, and that kind of things. And probably you may familiar with land speed record of the Internet 2 community. And then probably this group is basically doing getting the award, reaching the record every time by themselves, and they created the one record, and they kind of renewing the new record. And now this is for the V6 thing. V6 for the single stream and the multiple streams, and then this is reaching to the 8 bit per second, and then this is 99% of the one capacity. So it's basically the reaching to the maximum speed for the 10 Gbps pipe. And it was, by the way, achieved on the very last day of the last year, 2006, December 30 and the 31st. Basically, this is a land record, and then basically, as I mentioned, this contest competition is over for the 10 gigabps thing. So then, both IP versions 4 by version 6 achieving that kind of speed. And then, so it's a kind of a multiple TCP streams for the computer, access and the element access. And then, so the things like iSCSI type of application, accessing the storage, accessing the memories around the globe is one of the images we've been having. And so basically what I'm telling about this diagram is this is basically CPUs writing using the bus and then writing to the storage or accessing the memories. But the only different from the existing computer is like you see the Pacific Ocean and the Atlantic Ocean in the middle of the computer architecture. So that's basically the story, right? And that's the images about what we've been working on. The wireless and in the air, the light, using the light to pass the digital data. So our space is filled up with the digital data. And the control, sophisticated control with IP and the internet technology. And then also the entire globe is going to be, within the reach. And then what is a requirement then? And so the new requirements we see is basically I received a phone call, and because Wide Project is running some various kind of exchanges, and internet exchange, Lambda exchanges, and everything. So the people would see that the Wide Project domain name when they are doing the trace route or anything, and then the game user these days, kind of calling my secretary, and then with a loud voice. He was obviously mad, and he lost the game. And he lost a game of an internet game, and because of the latency you are creating. So Wide Project is bad because creating the latency in the middle of the data. And so this was a very happy phone call I received because now the normal people cares about the latency of the internet. And so the 200 milliseconds. This is a very important number. So let me see one of the, let me see, how can I manage? Look at this. Okay, this is a very short video clip. And this is a kind of a medical knife. And connecting to the various things, but using the laser effect. And then this detect the blue, this is showing the blue laser. So detecting the yellow things, anything on the top of the knife. So if you are using this knife, then there is a kind of a counter force you feel by the knife. So you cannot go forward. So it's like, cutting the peach, and there is a seed, very hard seed in it. And so you cannot move the knife forward. So look at this. This is a boiled egg. And then, so basically, this is one of the device we are working together. This is Inami-san and the Professor Tachi of University of Tokyo who's been working on. And now Wide Project has been working together with those people of the newly created controllable devices. And then, this is basically the future application is going to be of this kind of device is going to be obviously for the medical doctor, cutting some kind of a very important organ of your body. And then, if some kind of the material or color or whatever is going to be, changing, and then you cannot cut beyond that point. And even if that is a very soft and everything. So that kind of a control would be very important for the the medical application, for example. So technology is there, and they really want to use for the various applications like the distance medical applications, there's remote surgery and everything. So we've been having a lot of discussion with those researchers of the newly created devices. So the robotics and those people, virtual reality. Professor Tachi mentioned after this work, and to me that when the brain is reacting, and then we really need to reach the 200 millisecond, or a little bit less, between the 550 to 200 millisecond is a kind of a reaction of the human being. And then, the latency within, up to the 200 milliseconds could be acceptable in terms of the remotely providing this kind of a technology. So, that is a that is basically what I'm talking about with the 200 millisecond things. So when we talking about the globe of the space for the networking networking technology things, and latency is reaching to a 200 millisecond. Is that possible? And then yes, it's possible because 133 milliseconds is the speed of light around the world. And the 200 milliseconds is a kind of within reach of ours because of the, adding some kind of overhead. And then the 200 milliseconds from any point on the Earth to any point on the Earth could be, with a round trip time, it could be achievable because, again, I said 133 milliseconds is the speed of light around the world. Okay, so when we are working on a fiber around the globe, then we should really think about this number. And then the interactive applications around the world could be achieved by our research result. So this is one of the goals WIDE project is aiming at this point, working together with those interactive application people and latency-sensitive applications. And this is very interesting. So I started with a talk about I came from a far west. And then when I reach Europe, my data is going to pass around the United States and reaching here. And coming back, okay, can we reach between you and me, Europe and Japan? Can we make the RTT of a 200 millisecond this way? The answer is no. We need a direct topology, the sophisticated topology. Otherwise, we cannot make the 200 milliseconds. Well, I kind of thank God when He created the Earth. He created this size. If the Earth is a double of the size, we cannot make it. So I cannot work. So this is a very good size. And this is your view. This is your view. Our view used to be, yesterday. Let's state this way. Okay, this was our view of the networking of the world and the R&D networking of the world, right? Okay, so since we now understand that 133 milliseconds to reach. So this is my view of the R&D network. This is an R&D network from the above, and the blue line is what this one is talking about. Okay, is this enough? And so we really need a cable in here, and also inviting the edge. We really need a cable in here. So this is basically what we would like to achieve, and then I'd like to ask you, all of you, to help. And otherwise, this is not the network we are aiming at for the future. From year 2007, instead of this view, I'm sorry, for this one. This is a great picture. This is probably Max Brown, right, who wrote this picture. But yeah, was very nice. But now we want the circle, and to make that 133, 200 millisecond things. So the latency sensitive, to accept the latency sensitive application, and then also the words should be equal. So it's a long way to go, but the fiber shortest distance to most of the major cities is going to be very important. It's not very easy, but if I'm very happy if you could understand this concept, and then if you could work jointly around the world of the research networking people to talk about the kind of the shortest distance of the fiber should be installed, starting from us, and then eventually, as I mentioned, the people will use it. And the people will, all the interactive application will use it. And then the human beings going to be communicating anyway on the earth. And then this is basically what we are talking about. So when we are starting from the R&D network, and then the fiber, light paths, and a lot of discussions going on during this Terna thing. And then, also the inviting the Europe, and then, I think now it's really important that, working between the European networking community and the Asian networking community working together to cover this part of the surface of the globe. So this might be, not only a networking research topics, but also the computer research topics. Thank you very much.
I think we have time for a few questions. So, who wants the floor?
Thanks a lot for your nice geographic view. I'm just happy to let you know that what you call the northern route through Siberia, that's a 2.5 gigabit link fully operational. You can have an individual 1 gig lambda if you want. And also what you had, the yellow route, the southern one via India, that's also operational. It's financed by Australia, Korea, and the Europeans. And the northern one is jointly with the Chinese. So, welcome. You're fully in line with your research community.
Thank you very much. That's really now, I really want to see something happening during year 2007 and 2008 for the kind of testing of that kind of a latency change around the world, and especially between the Europe and Asia.
Any other questions?
Okay.
It doesn't seem so. Then I'd like to thank again Jan Murai for his excellent presentation.
Okay, thank you very much.
And it's now time for the coffee break, which will be in the other building. Thank you.